All right, so in the first part of day one lecture here, we're going to take a look at classes and inheritance, which are the key ideas in so-called object-oriented programming. So the idea of a class is that it's a programmer-defined data type. The language comes with low-level scalar data types, int, float, bool, str, and it also comes with several higher level collection types: dict, list, set, tuple. Those are in effect predefined classes at a slightly higher level than the scalar data types. And Python allows us to define even higher level classes of our own. So the idea of a class is that it encapsulates together the data attributes that describe the state or knowledge, if you will, of some kind of object, together with the methods or the functions that provide the behavior for the object. Now, what in the heck am I talking about? We tend to think of the low-level scalar types in Python as being passive data, if you will. And we tend to think of the arithmetic and equality, inequality, relational, logical operators as things that work on this passive data. But actually, it makes more conceptual sense to think of these scalar types as owning certain of these operators. That, for example, the int data type comes with arithmetic addition, division, subtraction, multiplication, exponentiation. It comes with the equality test, the less than test, the greater than test. And these operations that the int data type comes with use the same symbols, but are not really the same as the operations that come with the float data type. What do I mean by that? Well, if I take an int and another int and I use the plus symbol, that plus symbol is doing addition conceptually, but internally it's actually doing integer addition. And internally within the machine, integer addition is a quite different thing from floating point addition. Conceptually, they're both addition, but the internal mechanism that happens when you add two ints versus when you add two floats versus when you use that plus sign to add two stirs, which is actually a concatenation operation, those are three different operations. So it's a good idea to think of the data types as having the operations that operate on them. And a given operation symbol, or a given function name for that matter, will perform some different behavior on these different data types. So we can define higher level data types that use things like ints, floats, bools, lists, tuples, sets internally to maintain their so-called state information. And we can associate with that class operator symbols like plus, star, slash, double equal, as well as function names like .insert or .sort or .pop or things like that that cause these objects to behave in some certain way. Okay, so in other words, the idea here is to put the primacy of our thinking on the data as objects that have behavior as part of them. And encapsulation is the magic word that's used for this idea, is to encapsulate together the state information and the behavior. Basically, our idea here is that we want to bring the level of the language up to the kinds of problems that we're working with. So if we're doing financial programs, we want within our programs to be able to manipulate things like stocks, bonds, yield curves, risk models, etc. We don't want, as we would have to do in a top-down functional decomposition world, to take our concepts of calls and stocks and bonds and have to push that down through a layer of functions to get to the low-level ints, floats, lists, sets, and so forth that actually implement the details. What we want to do instead is to pull those low-level data types by encapsulating them in well-defined classes up to the level that we want to conceptually think of and program at. Another thing that classes provide, which historically is what separates so-called object-oriented languages from object-based languages, is that object-oriented languages provide inheritance hierarchies. That is, we can directly describe is a kind of relationships among the data types that our program is using. For example, in finance, we worry a lot about how to calculate correct prices and risks of various kinds of options. We have call options that give you the right to buy some underlying asset like a stock or a bond at a certain price. And there are certain kinds of calls that specify when and under what conditions you're allowed to make this decision to buy the underlying asset. For example, a European call only gives the opportunity at the so-called expiration date to decide whether to buy the underlying asset or not, whereas American calls, Asian calls, other kinds of calls have different rules about when and under what circumstances you're allowed to exercise the option and buy the underlying asset. So, in a nutshell, a European call is one kind of call, a call is one kind of option, and Python allows us to model this as a kind of relationship among these things. In an inheritance hierarchy, we call a method polymorphic if that method has the same interface for various kinds of classes in a hierarchy, but behaves differently depending on what specific kind of object it's invoked on. For example, any kind of well-defined option can have a price computed for it, but the details differ enormously depending on whether the kind of option is a European call versus an American call versus a European put, an American put, or various other kinds of options. So price here would be an example of a polymorphic method whose behavior varies depending on what specific kind of option it's applied to. Now, here again, I just want to point out that in addition to encapsulation, when you're talking about object-oriented programming, this idea of inheritance and the idea of polymorphic methods are important. You will be expected to have heard those terms and have some idea what they mean. All right, so forgetting about this theoretical, conceptual stuff, encapsulation, inheritance, polymorphism, what does it mean to us in pragmatic terms when we're writing Python code? Well, if you have a well-designed class, that class is going to provide a clear and coherent interface that makes objects of the class easy to use. For example, the list built-in class does have a very clear and coherent interface consisting of a combination of symbolic operations and named methods. This interface is non-trivial, but it does have a certain clarity, coherence, consistency that makes it relatively easy to learn and remember. This is going to make life a lot easier for unsophisticated application developers who are generally at a lower level of expertise compared with the class and module developers who are developing the libraries that these application developers use. The class reveals everything that an application developer needs to know in order to be able to interact with objects of the class, but the class also hides internal implementation details that the application developer should not be concerned with. For example, if you're developing a graphical application, you know that you're going to need to be able to display shapes on the screen. You know that you're going to want to do things like scaling them, rotating them, translating them from place to place. But as long as what happens is well defined in the interface, it should be irrelevant to you as a user whether the person who implemented this geometric shape class hierarchy chose to use Cartesian coordinates or polar coordinates internally. You as an application developer using the class really shouldn't need to know or care about those internal details. Another nice thing about a class is that initialization of objects is handled in a clean and consistent way, so you don't end up with improperly initialized objects in your program. For example, you don't end up with a European call option that has no underlying asset associated with it. All right, so let's get into the details of how we go about defining and using classes in the Python language. So half of our job when we define a class is going to be to define the methods that provide the behavior of objects of the class. These methods are simply function definitions, and each method automatically receives a reference to the current object itself. You must define each method within a class to have at least one parameter that refers to the object itself, and purely by convention, but it is quite universal and people would be puzzled if you didn't follow this convention, that first argument is named self. Now, any Python class is going to have at least two methods in order to be of any use to anyone. The first is a so-called constructor method that creates an object belonging to the class. And the name of that constructor method for any Python class is always __init__. In addition to the self parameter, which should be the first parameter to the init method, you can then pass additional parameters to initialize the remaining internal state of the current object. Well, so that allows you to properly create and initialize an object. Now, if you want to see the object on the screen, you're also going to pretty much have to have an __stir__ function that converts the internal representation of the object into a human readable string that could be displayed, for example, using the print function. When you call the conversion or creation function stir on some object, it turns out that that stir function call is converted into invoking the __stir__ method on that particular object. Okay, so let's turn this into some concrete example. Let's suppose that we're creating an application in which we're going to need to have employees. Well, we think about what an employee needs to have as far as its internal state, and we might decide that each employee is going to have a name. Each employee is also going to probably have an employee ID number. So if we have two different Robert Smiths, we can tell them apart from each other by their unique ID number that was assigned to them when they were hired. And each employee, unfortunately, is going to have to be paid, so we'll need to know what the hourly pay rate is for each employee that we hire. We're very likely going to need to know lots of other things about the internal state of each employee object, but we'll start with these three internal state variables. Okay, so on slide 6, this is what each employee is going to have to know about itself. Now, in terms of what each employee is going to have to do as far as behavior, well, we need some way of creating a new employee. That is, we're going to hire people. We also need to be able to see a human readable representation of the employee. That is, we're going to need some way of converting an employee object into a stir that we can print, let's say. We're also going to want to have some means of giving an employee a raise. Okay, in real life, we're unfortunately not going to be able to hire somebody at a certain hourly rate and then just leave them at that same hourly rate forever. If we try to do that, they will get annoyed and leave eventually. Again, there are probably lots more behaviors that we're going to want to be able to have each employee perform, but these three are enough to begin with. Let's look at all of this now in Python code. Here we go. We define a class in Python by saying the keyword class and then the name we want for our class. In this case, that's employee. And then we have a colon following the name of the class, just as we would if we were defining a function or writing an if or writing a for or what have you. Nested within the employee class are definitions of the three methods that we said that we want. We have our __init___ method. Notice that it takes self as its first parameter. In fact, each of these methods takes self as its first parameter. And then these additional parameters, name, ID, and rate, are stored in the current employee object itself in a field called underscore name for the name, a field underscore ID for the ID number, and a field underscore rate for the rate. Now, I will just tell you right now that one of the things that you're going to have the most trouble getting used to here when you're defining methods for a class, when you're new to this, is you're going to forget to say self as the first parameter, and you're also going to forget to say self dot in front of each of these attribute or so-called instance variable names. Okay, so when you're writing your first class and Python yells at you, I suggest you make sure that you have self as the first parameter and that you're using self and a dot in front of each state variable or instance variable name. All right, so in addition to our initialization function, we're also going to define the underscore underscore stir underscore underscore function that returns a human readable string describing the employee. And we have the give raise method definition. But let's jump ahead for a moment to see where this initialization function comes into play. Now, I have this already typed into a Python module file, so let me open that file. Okay, so here is my code file. The name of this module file is employee.py. It contains the class definition for employee. And I hope you recall from the prep course that we can use underscore underscore name as a way of identifying whether this is the current module or not. Okay, so if this is the current module, that is, if this is the main module, then all of the code in the section of code below the if name equals main decision will be executed. And the way that I create an employee is to call this method employee, that is, I use the name of the class as a function, and I provide whatever state information an employee is going to require. Now, each employee, we said, is going to have a name, which will be a string, an ID number, which will be an int, and an hourly rate, which we'll use a float value for with 2 digits after the decimal point. All right, so when I say employee and then parentheses John 1 60.5, that ends up calling the employee class's init function with a reference to the current object that's being created as the first parameter, and then these 3 values that I've passed in, John 1 and 60.5, as these trailing 3 parameters. Okay, so the name that was passed in, I'm going to store into an attribute of the current employee called underscore name. And the ID that's passed in, I'm going to store into an attribute named underscore ID. And the rate I'll store into underscore rate. Each time I create an employee object, that new employee object is going to have its own copy of the underscore name and the underscore ID and the underscore rate attributes. So here, when I say employee John 160.5, that creates the new employee that I'm referring to with the variable John. And later down here, when I say Ed gets employee Ed 272.25, Ed has its own underscore name, underscore ID, and underscore rate attributes. Okay, so that's where the init function comes into play. When you create an object by using the name of the class as a function, that automatically invokes the underscore underscore init underscore underscore function for that particular class. And the argument values that you pass in become the parameter values of the trailing parameters, and you typically will use those to establish initial values for the internal state, so-called instance variables of this current employee object that we're creating. Okay, the next statement that's happening here is a print statement, print function call, where I'm calling the stir function on John to get a human-readable string describing John, at least I hope that's what I'm going to get, that I can then display on the screen using the print function. Well, this stir function call, as I said, gets converted into calling this underscore underscore stir underscore underscore function, and John will be the self object in this case. What I need to do in this underscore underscore stir underscore underscore function is to return a string representation that describes John. So I'm going to say that the ID is, and then I'll convert that integer ID number into a stir. Remember that plus for stirs is concatenation. So I'm going to have ID 1, comma, name colon, John, comma, salary colon, and here I'm using format to get a floating point number with exactly 2 characters after the decimal point to represent John's rate. Now, when I run this program, okay, slide 8 is my class definition. Slide 9 is the test code. And when I run this test code, what's going to happen here is that John is converted to a stir. That stir is then printed. And my output looks like ID 1, comma, space, name, colon, John, comma, space, salary, colon, 60.5. All right, let's confirm that. I'll actually run this module now by pressing F5. Okay, now I was a little suspicious when I looked at my slide here on slide 10 because I did request 2 digits after the decimal point. So what actually comes out is 60.50, which makes more sense as an hourly rate than 60.5 does. Okay, so that's the init function, which is invoked when we create an employee object, and the stir function, underscore underscore stir underscore underscore, which is what gets called when we use the stir top-level function. It turns out that when you print an object, the print function itself actually calls stir on each one of its arguments implicitly. So it's actually redundant for us to have called stir ourselves. We could have just said print John, and that's equivalent to saying print stir John. And that's why we get the same line of output again here. Continuing in our program, we create another employee. This employee is named Ed. ID number is 2 and hourly rate is 72.25. We print Ed. Then we give Ed a raise. So this is going to call the giveRaise method. And what we're going to do is modify Ed's underscore rate attribute to be its original value times 1 plus the percentage over 100. So if the percentage is 10, what I really want to do is to multiply Ed's current rate by 1.10. So in other words, 1 plus 10 100s, 1.10 will give me the new rate. And when I print Ed again, I will see the second time I print Ed that Ed has been given a 10% raise. Okay, so that's a very simple example, but it does illustrate the idea of defining a class, defining 3 methods for that class, importantly including the init method as well as the stir method, underscore underscore stir underscore underscore. And in this case, we also have a third method called giveRaise. Many object-oriented languages, such as C++ and Java, have what are called access specifiers that prevent code outside of a class from messing around with the attributes inside of a class. This is not the case in Python. In Python, all of the class attributes are accessible from any code. That is, in C++ or Java terms, if you're at all familiar with those languages, everything in Python is public when it's inside of a class. Now, by convention, Python developers treat any attributes whose names start with an underscore as private. And by convention, the language does not enforce this in any way. By convention, application programmers will not directly tinker around with attributes in classes whose names start with an underscore. But as I said, the language does not actually enforce this rule. So if I wanted, as an application developer, to compare John's pay rate with Ed's pay rate to figure out which one of them is making more, there's nothing that prevents me from saying John._rate to access the rate attribute within the John object. And likewise, there's nothing preventing me from accessing Ed_rate, Ed._rate, to find out Ed's pay rate. So this code is fine, and in fact, it's what we have on the in the bottom part here of our employee.py module. It does not respect the implicit privacy that we've requested as the class developers by using the underscore, but it will run because nothing really is private anyway. And so here we see that the comparison is performed, and we discover that John makes less than or equal to Ed. What does this mean? Well, one thing it means is that as a class developer, you have to anticipate in advance which attributes outside developers might want access to, so that you can give them an approved interface, if you will, for accessing those attributes. This typically involves creating a bunch of set and get functions that allow you to modify attribute values within objects or to simply get attribute values from objects. Now, in this particular case, we're dealing with employees, and it is possible for an employee's name to change. They can do that legally, they can get married, they can get divorced, what have you. It's also possible for the employee's rate to change. There's no keyword, unfortunately, that allows us to establish rate as an upward-only changing attribute. It can go both directions. However, typically when a company hires an employee and assigns an ID number to that employee, that ID number will never change throughout the employee's existence with the company. In fact, even when the employee departs the company and other people are hired into the company, it's very likely that nobody is going to be assigned that same ID number that was already used by that previous employee. So we have chosen not to create a set function for the ID, and we're hoping the fact that we did not establish a set function and the name of the ID attribute starts with an underscore is enough of a hint to application developers that they should not fiddle around with the ID number. Here's what the set and get methods look like. We have two set methods that allow us to modify the name and modify the rate. And we have three get methods that allow us as application developers to get the name of the current employee, or get the ID, or get the rate of the current employee. These definitions of these functions are extremely simple-minded. You'll notice that when I set the name or when I set the rate, there are no checks being performed to make sure that the new name or the new rate make any sense. That is, if I have the employee John and I say John.setName, and then I provide, let's say, a floating point number, this implementation of setName will naively establish that floating point number as the name for John. So to make this more robust, we should add some checks. that the new name being requested is at least some kind of string, or that the new rate being requested is at least some kind of positive floating point number. But we're not adding those checks in this case. We're just illustrating the idea of sets and gets. And here is a revised version of this code that compares John's hourly rate to Ed's hourly rate using the approved interface functions, the get functions. So we're calling get rate on Ed and we're calling get rate on John, and we're also calling get rate on Ed, and then we're comparing those two, and then we're using get name to get John's name and Ed's name. So this is now respecting privacy by using the interface functions. I do have a file that implements this revision of the code named employee2.py. Here is employee2.py, and you can see that it's the same as employee.py, but we have added the two set functions, we have added the three get functions, and we have revised the code comparing John and Ed's rates to use those get functions rather than directly accessing the attributes. The attributes that are associated with an individual employee object, or that is to say the attributes that are associated with a particular instance of an employee, are referred to as the instance variables for that object. So John, which is an employee object, has an underscore name, an underscore ID, and an underscore rate instance variables. Ed likewise has underscore name, underscore ID, and underscore rate instance variables that are separate from John's. It is entirely possible to have a variable that belongs to the employee class as a whole. This is referred to as a class variable. Let's take a look at how to set up a class variable and why we might want a class variable. Okay, so the existence in the initial value of a class variable is established outside of any method definitions. Typically, this is done right at the top of the class before any methods have been defined. So, for example, let's suppose that we want to keep track of how many employee objects have been created since the program started running. Well, here is a class variable called numCreated. Notice that it is defined within the employee class, but outside of any of the method definitions. In this case, we've defined it above the underscore init underscore method definition, and we've established an initial value for numCreated of 0, which makes sense. When the program first starts running, the number of employees that have been created so far is 0. Then, each time an employee object is created, like when we say employee John 1 60.5, and when we later say employee Ed 2, 72.25, notice what we've done to the init function here. We've modified the init function so that the last statement in the init function increases the number of employees by 1. And notice another important thing here, which is that although underscore name is an attribute of self, and likewise underscore ID and underscore rate are attributes of self, numCreated is an attribute of the employee class as a whole, not of the current employee object that I'm currently creating. All right, so we don't say self.numCreated, we say employee.numCreated. And plus gets 1, of course, is going to add 1 to that. When we want to find out at some point in our program how many employee objects have been created, we can either say className.numCreated, or we can say objectName.numCreated. We can access that numCreated class variable either through the class name or through a particular instance of the class. All right, so in my program here, where I am creating an employee named John, and another employee named Ed. If I then add these two print statements, I'm going to get the number 2 displayed twice. Once when I access num created through the employee class, and once when I access num created through the John object. Now, really, this class variable num created should be private. And so to make it private, or at least to attempt to make it private, what we should do is to use the underscore in front of this class variable's name and establish a get method that can be called in order to obtain the value of this num created variable. So let's take a look at those improvements. All right, here we're going to add our underscore to indicate to someone looking at this class that num created should be respected as a private variable. Of course, we have to modify where num created is incremented in the statement in the init function. And here we have added a getNumCreated method that will return the numCreated value from the employee class. All right, well, that seems reasonable. This, it turns out, has a very subtle bug, because when I say John.getNumCreated, well, John is an employee object, and so if I flip back to slide 21, I'll see that John is self in this case, and I am successfully able to find out what numCreated is by using the getNumCreated method on John. That works fine. But if I try to use the getNumCreated method on the employee class, I get yelled at. I get told that I am missing one required positional argument, namely self. Okay, because employee is an entire class of objects. It's not an individual employee object, so there is no self passed down to getNumCreated if I invoke getNumCreated on the class as a whole. So that seems like a step backward. It appears we can find out how many employees have been created if we have an employee object that we can ask. But we really would like to be able to ask the employee class how many employee objects exist. Well, here is a sneaky workaround. We can treat the self parameter in our getNumCreated as a keyword parameter with a default value. All right, this way, even in a situation where I don't explicitly pass in a self object, there will nevertheless be a self parameter whose value is none. And if you take a look at the return statement in the implementation of this method, I'm not really using self anyway. I'm just saying employee._numCreated. That little trick there will enable both getNumCreated invoked on a particular object to work, because self in this case is John, and it will also enable getNumCreated invoked on a class to work, because in this case self is equal to none, but self is being ignored, and so all is well. Okay. So now we have got a little more consistent behavior with having our class variable be private, just like our instance variables, our per object attributes being private. I do have a file, employee3.py, that implements this private class variable _numCreated. All right, well, the last thing we're going to look at here in this lecture is inheritance. The idea of describing one class as a kind of some other class. As an obvious example, we have an employee class that we've been working with, and a manager is a kind of employee, but a manager also has some additional knowledge that regular employees don't have or don't need, and some additional responsibilities or behaviors that employees don't have. A manager is going to inherit all of the attributes and methods from the employee class, but the manager will add its own additional attributes, that is, additional instance variables, as well as its own additional methods. Here we have our employee class being imported with the abbreviation EMP, and the way I specify inheritance in Python is to say class manager, and in parentheses I specify the class that the manager class inherits from. So the manager class inherits from the employee class described in the EMP module, that is, in the employee module. The manager class, like any class, is going to need its init function and its stir function, and it will need whatever additional methods are unique to the manager class. In this case, we're going to say that a manager has a budget to keep track of, so we will have a set budget method and a get budget method associated with the manager. Other than that, a manager is going to be like an employee. And in fact, when we initialize a manager, self is going to be the first parameter for the manager that's currently being created. Name, ID, and rate are going to be the next three parameters. And notice what we're doing with these. What we're doing with these is we're passing these down to the so-called superclasses init function. Now, a superclass is like a superset in the sense that the set of all employees includes the set of managers as a subset. So the employee set is a superset of the manager set, if we think of these things as sets. So consequently, what we're doing here is we're passing the name, the ID, and the rate down to the init method of the superclass, which is the employee class. And so the name, ID, and rate attributes, that is technically the underscore name, underscore ID, underscore rate, instance variables within the employee part of the manager, will be initialized with these name, ID, and rate values. And then finally, the last parameter here, budget, is simply stored in the manager's own underscore budget instance variable. To convert a manager object to a string that can be read by a human, we've been careful about how we organize the stir function at the employee level. So we can use super again in the implementation of this underscore underscore stir underscore underscore function for the manager class. And we can say, all right, let's call the superclass's stir function, which will return to us the employee part of the manager, represented as a stir. And we're simply going to add on comma space budget colon and then the budget that this manager is responsible for keeping track of. Okay, so with that manager class defined, we can now test it. Let me open my manager.py module. All right, here's my manager.py module. I'm importing employee 3, my most up-to-date version of the employee class, as emp. And I'm then creating the manager class. And down here I have some testing code. I'm going to create an employee named John and an employee named Ed, just like I did before. Below there, I'm creating a manager called Ann. And notice that the manager constructor function is being passed Ann's name, Ann's ID number, Ann's hourly rate, as well as the budget that Ann is responsible for. When I run this program, the information about the employee John is displayed. Then the employee Ed is displayed both before and after Ed gets a raise. And finally, the information about the manager Ann is displayed. Okay, so that completes our introduction to classes, as well as the idea of inheritance, and some of the important components that you need to use when you define a class of your own.